You're looking at a famous cartoon. It's actually quite old. I think it goes back 18 years now. And this is a sentiment that is often expressed by people who don't quite understand how policy works. There's of course people who say that climate change is just a load of nonsense, right? It's all a conspiracy or a hoax, and therefore we should not worry about climate policy at all. And then some environmentalists turn around and say, but even if climate were a hoax, then we would still have good reasons to do climate policy because this would lead to energy independence, this would preserve rainforests, it would lead to green jobs, livable cities, renewables, clean water, healthy children, and so on and so forth. And therefore, regardless of whether or not there is a climate problem, we should do climate policy. Is the argument. This is a bizarre argument, and it's also just it's just very strange things to say. In the more serious literature, outside the world of cartoons and silly environmentalists, there's a lot of people who claim that there are secondary benefits of climate policy, and therefore we should do more about climate policy. And one thing that is, well, the things that are listed here are often mentioned, and for instance, an argument that you hear nowadays quite a lot is that the air in China and India is foul, and it's hard to disagree with that, and that needs to be cleaned up. That is, we want to improve urban air quality in Beijing and in Delhi and Shanghai, and therefore we should reduce carbon dioxide emissions. The air pollution that you would indeed find in those cities are caused by sulfur emissions and nitrogen emissions, ozone, and so on and so forth, rather than by CO2, right? So these are the classic urban environmental problems. There's also a lot of particulate matter about. And some people seem to think or hope, a lot of people seem to think that there is a reason China and India will embrace climate policy. And what I'm going to do, and I don't know how long it's going to take me, is take you through these arguments. And one of the reasons that some of this is so silly is because Tim Bergen sorted this out in his 1954 book. But apparently some people suffer from memory loss and have forgotten about books that are sort of like more than 60 years old now. So the very fact that we're talking about secondary benefits means that we're talking about two things we care about, at least. There's two problems that are somehow interconnected. And therefore I'm introducing here two criterion emissions, G and A, where G stands for greenhouse gases and A stands for air pollution. And actually put everything in the emission reduction space rather than emissions. And the total social benefits of emission reduction are assumed to be linear. That is, our total welfare gain if we reduce air pollution is alpha A, and our total welfare gain if we reduce G is chi G. Right? And that's the first equation that you see there. Problems have to be interconnected, right? Otherwise it doesn't make any sense to say, well, one is a secondary benefit to the other. And I do that through the emission controls. So G, the amount of greenhouse gases reduced, is our emission reduction effort for greenhouse gases, that is rho R, as well as our emission reduction effort for air pollution at pi S. And for sanity, I assume that the rho is much greater than the pi. That is, if we want to go after greenhouse gases, it's best to reduce greenhouse gas emissions directly rather than reduce air pollution directly. And then ditto for air pollution, which is our air pollution control effort, sigma S plus our greenhouse gas emission control effort, tau R. And again, for the sake of sanity, I assume sigma is much greater than tau. And then the costs of emission reduction are a simple quadratic function, half times kappa x squared plus half times lambda r squared. And so far, I just introduced notation, right? Just a couple of equations. If we substitute the second set of equations into the first equation, then we have essentially we substitute A for sigma s plus tau r and G for pi s plus rho r. We get the equation that is at the bottom, and then you can revert that to make that into a function of s and r. And of course, those are the things we choose, so it's handy to gather the coefficients for s and r. So we have an expression for the benefits of emission reduction in S and R. We have an expression for costs of emission reduction in S and R. One is B, the other is C. And then we can work out what is the optimal control for R. That is, at what point do the marginal benefits, the DDR, equal the marginal cost, the CDR. And what we find is that the benefits equation is of course linear, so we simply end up with alpha tau plus chi rho. There's no r involved, right? So that just becomes a constant. And then the optimal emission control, the marginal cost of emission reduction is first partial derivative of half and lambda times r squared, and that of course 2 cancels against the half, so we end up with lambda r. And then our optimal rate of emission control is the expression you see there, alpha tau plus chi rho over lambda. And here indeed we see the argument that I started off with. So if we go, well, we can go back to the equations, right? What we find, our concern about climate change is measured by chi, right? That's where the benefits come from. So if chi is 0, then the optimal rate of greenhouse gas emission reduction is still positive, right? It's alpha tau over lambda. So even in the absence of a climate problem, we would want to reduce greenhouse gas emissions. And of course, the more we care about air pollution, and that's measured by alpha, the more greenhouse gases we want to reduce. So there is indeed a secondary benefit, and there is indeed in this framework a reason to reduce greenhouse gas emissions, even if climate were no problem. And then similarly, in that what you see at the very bottom, you would also want to increase your efforts, or at least change your efforts, depending on the signs of chi and pi, your efforts to reduce conventional efforts. So the two problems are interconnected, and the optimal control of one, or our concern about one, affects the emission reduction plans for the other. But now hold on for a minute. I work in a very simple linear quadratic framework, which may be appropriate for climate change, but may not be appropriate for air pollution. So let's replace the a that we saw previously into the square root of a. So essentially what this says is that the benefits of avoiding air pollution saturate. Instead of just continuing to go up, and the more and more particulates you take out of the air, the more benefits you get. It's still the case, right? But now it actually it plateaus, it flattens off. And that is how we think of air pollution, right? I mean, if there's a lot of smog in the air, then a lot of damage is done. Once you sort of like reach the pristine airs, the almost pristine airs of a city like Amsterdam, you can take away more air pollution. People here are not dropping like flies, right? Yeah, there's a bit of additional lung cancer because of the stuff that is in the air, but it's not like we are in Beijing, that people are simply dropping dead. Or like Amsterdam used to be, or definitely London used to be in the 1950s, right? We're nowhere near that situation. So it sort of makes sense to say, well, we drive up our control of air pollution really, really high, then the benefits just become smaller and smaller and smaller. The same is not true instantaneously for greenhouse gases. Because greenhouse gases are sort of, or the benefits of greenhouse gas emission control. Climate change is driven by emissions over long periods of time, over a large number of emitters. They're approximately linear, and if we push emissions down further and further and further in one jurisdiction during one term in Parliament, it's not going to really affect the climate problem. So there we can safely assume, I think, that our benefits are roughly linear in G. So that is the change in equation, right? We simply inserted a square root sign. Emission controls are still the same. Those gradients haven't changed. The cost of emission reduction are still the same. So if we insert the second set of equations in the top one, we get roughly the same thing, but we have a square root inserted. So that's our benefits of emission reduction. Cost of emission reduction are still the same. Optimum control is the DDR, should equal the CDR. The CDR is the lambda R, so that is unchanged. If we now take the first partial derivative of our benefits equation to R, we still have the term chi rho there, just as we had before. They're kept us not concerned about climate change. We still have the alpha tau that kept us not concerned about air pollution, but now we should divide that by 2 square root sigma s plus tau r. Now we have a bit of an awkward solution, right? So now we have as an implicit function for optimal emission control that r prime equals alpha tau as it did before plus chi rho over lambda, but we also have the awkward complication of having sigma s prime plus tau r prime there. And there's actually no generic solution to this, because we also need to have a very similar equation for sigma prime, for s prime, sorry, and it's actually hard to come up with a generic solution to this. But we can say something about the properties of this equation. So, since the first term, as long as tau is positive, that is, if we reduce greenhouse gas emissions, we also avoid some air pollution, and we care about air pollution, alpha is positive, then what we do find is that there's indeed a secondary benefit. That the fact that if we reduce greenhouse gas emissions, we switch away from coal to gas, and as a result, we put less sulfur in the atmosphere. If that happens, then indeed we should switch more from coal towards gas than we would do if we were only concerned about climate change, if we were only concerned about CO2. So that holds. The secondary benefit is still there. At the same time, we see that R prime negatively depends on S prime. That is, the greater S prime, the more we control local air pollution, the lower the secondary benefit, and the lower the additional effort we need to make to reduce greenhouse gas emissions. And the same holds for S prime. And that, of course, takes away a bit of the concern, or takes away a bit of the argument about secondary benefit. If we worry about climate change and we worry about air pollution, but through air pollution policy we take away a large part of the air pollution problem, then the additional bit of greenhouse gas emission reduction that you would do becomes much smaller, right? And that goes back to Tim Burton. If you have two problems, climate change and air pollution, you should need two instruments: greenhouse gas emission control and air pollutant control. Now, what happens if climate change is a hoax, right? If either climate change turns out to be completely untrue, or it turns out to be not affecting our welfare at all, right? And both would result in chi being equal to 0. What happens to these first order conditions? Or, still first order conditions rather than optimal, right? So that's our double prime. So essentially, the second term drops out. Everything that has a chi in simply becomes 0. What we have is still, we want to do a little bit of greenhouse gas emission control, because it would also avoid air pollution, but much less than we would otherwise do, right? Because we did assume that the rho was much greater than the tau. Now, what happens to our S double prime? It becomes smaller because the chi p over kappa is gone. But at the same time, right, because our R double prime has dropped so much, our S double prime is actually going up again. And the result is a little bit ambiguous. And of course, if S double prime is going up, then R double prime is coming down, because we take away the air pollution problem, and therefore there is less to worry about, and there's less reason to reduce greenhouse gas emissions. to solve another problem. So these arguments that people are making about secondary benefits and then being a good reason to reduce greenhouse gas emissions, even if climate change is a hoax, you start sort of working through the analytics. It doesn't really hold. Yes, there is a secondary benefit. If your climate policy reduces air pollution, or if your climate policy increases energy security, then of course we should do more of it. There is a real benefit there. But if you are so worried about air pollution, then solve it through air pollution. If you are air pollution policy, if you are so worried about energy security, solve it through energy security policies. And I mean, if we look at some of our air pollution problems, they are, for instance, caused by primitive engines, two-tact engines that you would see in motorcycles. The best way of solving that would be to go to a more advanced engine. It actually uses more energy typically. Or if you're worried about some of these things, you may want to put catalytic converters in your cars to take out, in your car engine, to take out some of the pollutants that come out. But those things take energy. They reduce the energy efficiency of your cars. But there are a lot cheaper, a lot more direct way of going after air pollution than through the clumsy way greenhouse gas emission reduction, right? Where essentially in transport we're talking about energy efficiency and energy efficiency only. So yes, there are secondary benefits, but no secondary benefits would never be a substitute reason to reduce greenhouse gas emissions by an enormous amount. Right? By a little bit, yes, but not by a lot.